The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Due to technical difficulties, only a portion of this lecture is available.
It's related then to the population in that as the state. So you would have to develop this populations. What are the changes in the United States population as a result of this? So it's a slight tweak, but you can basically use the same thing. Okay, so what did we find out? In general, what we're doing is we're going through formalism to start with, and then hopefully as we move along, clear up what it means in the first place. So the idea is nonlinear response functions take this form. I've just written second order because it just starts to get more and more painful as you go to higher orders. The idea is you'll see a form that involves nested commutators in the dipole operator. And we are looking at which means we're looking at a variety of correlation functions of the form that really just involve a sequence of interactions between the incident electric field and the matter separated by time evolution under a material Hamiltonian. So just to remind you, all this is derived under an interaction picture Hamiltonian of the matter and the light field. Out here for B being all the electric fields. So this is a super complicated thing. It's this dipole operator is all the charges in your system, and we haven't specified anything about what kind of light field this is. So this response encodes everything, every possible spectral range, and then what is this? What do these correlation functions tell you? One of the things that becomes very different with nonlinear spectroscopy compared to linear is that when you recognize that light creates coherences in matter, that the moment you have more than one light field, the moment you have more than one period that the quantum coherences can evolve, then you have to keep track of the phase of which coherences are evolved. And so this is really the difference between the different correlation functions that are in this response function. Because the way it plays out mathematically is that we talk about action of the dipole operator on the bottom of the density matrix. Instead, in another way, we're talking about does the wave function, do we evolve the wave function or its conjugate? In a sort of microscopic sense, what we're talking about is, just think a little bit about what happens when you create a wave packet. That there are two ways that this wave packet can evolve, and they just differ by the phase at which they acquire. They may propagate in one direction or the other. And the difference between those two things is a phase factor, but it also is different in terms of the momentum that the light is imparted to the system. Okay, when we're doing a semi-classical version, we've thrown away the light matter, the light part of the particle. But actually, you have to remember, look, the light has momentum. And depending on whether you have absorption and stimulated emission processes, this influences the momentum which you kick the molecules. And so, with a linear spectroscopy, you don't really need to worry too much about the state. But the moment you start doing multiple interactions with evolving wave packets, you better darn well keep track of the phase of where this thing is going. So that's the essence of this thing. All right. This is second order nonlinear response. I won't go to third order right now, although we'll spend most of our time there. But what I will point out is that in general, for perturbative expansion, you're looking at the nth order nonlinear response. You're going to get n nested commutators in this sequence separated by the consecutive time intervals. you'll have an IH bar to the nth power out here. What I left out of this is sort of the step response functions. These are just sort of, you have to remember to enforce causality, that these values can only take on positive values. And when you play that all out, what you realize is that there, for an nth order response, you will have n correlation functions, of which only n over 2 are independent. So that is here, for instance, here, second order response, there are 4 correlation functions, but 2 of them are just complex conjugates of the other. That means we write it as 2 independent functions, and they're complex conjugates. So this is good. Looks like a real function. It is directly proportional to observable. Okay, so what this all boils down to is for an nth order spectroscopy, you have 2 to the n correlation functions that you're going to have to keep track of. So for third order, you're going to have 4, and so on. And what we mean by that is those are potential levels of bookkeeping that you have to keep track of. Okay. So the complexity of the thing just escalates quickly, and this is part of the motivation then for going to diagrammatic perturbation theory. It's sort of now, given this very general formula, how do we apply it to a particular system of interest, and try and keep track of all the possible permutations and interactions that are going there. So that's sort of the plan today. What we're going here to start with, at least, what we're going to do is consider now the matter all of a sudden. And we'll just say that we know the eigenstates of the material entity. We'll call them ABC. I'll just, and we also know how the dipole operator then is expressed in these eigenstates. A little bit later on, you can sort of see this coming a little bit, is we're going to take a slightly different approach and split up the material Hamiltonian into 2 parts, one of which are the degrees of freedom of the system, the degrees of freedom that include that the dipole operator acts on, and then that will be the dark degrees of freedom that the dipole operator doesn't see, but which influence the system through an interaction. So we're going there, but at the moment we're just saying we know the full eigenstates of the system. Okay. So now what diagrammatic perturbation theory does is allow you to keep track of how a particular set of eigenstates resonant with the light fields that you decide to put in lead to particular signal contributions. And these diagrams, they're important from a practical point of view. You go into the lab, cross a few beams, and you just see some strange beam in some unknown color propagating in a background-free direction. And you want to understand what gave rise to that thing and what is that going to tell me about the structural dynamics of the system. And you basically want a way of back-propagating from what you saw, the signal, to what's going on. And diagrammatic perturbation theory helps you there. Okay, so we're going to, there's sort of 2 approaches to this.
Andre, can I ask a quick question just about the correlation functions and what you were talking about with enforcing causality?
Yep.
If you, let's say that you don't enforce causality correctly and you say that something, is that just saying basically that's equivalent to a different experimental system where the light pulses just come in a different order?
Yep, exactly. So what we'll actually work through an example probably later today, just like that. That is exactly right. That one of the things that you have to keep track of when you do a time domain experiment is the time ordering of your interactions. But even when you have a sequence of continuous wave fields all across the planet, what it means is that you do have to keep track of the possible permutations of interactions. And those are all accounted for in these correlation functions. They just amount to other orders of the dipole operator.
So does there have to be a difference if I have just say 2 light fields, and if I put one on first and then if I do it in reverse, is it necessarily different?
So imagine you have a second order experiment in which you have a 3-level system, and I have 2 fields that I'm going to put on this. I can put them on CW, or I can turn one off and then turn the other on. And there is a difference between whether I turn one on in this order or one on in this order. You know, I may be resonant in one state and not in another. And that completely changes the phase acquired by the coherent system. So in a time-domain experiment, you might select one of these. You might select a particular correlating function with that time order. In a continuous wave experiment, you would have to add contributions from all of these permutations. Okay. All right, so the idea is what we like to do is work with Feynman diagrams and ladder diagrams. These are sort of the 2 flavors of diagrams, each of which are meant to represent one particular sequence of interactions that goes on within one of these particular correlation functions. And just in general, sort of the way these would look is both of these refer to propagation of the density features, or said another way, watching the evolution of coherences within all the states of the ensemble. And in Feynman diagrams, the way this works is you begin with the state at equilibrium, and you draw a couple of bars, and these are meant to represent the 2 sides of the density matrix. You may start in a ground state population. Time moves upward in this diagram, so the sequence of interactions moves upward. And then we draw little inward and outward going arrows that signify absorption or stimulated emission events. And these are separated in time by a free evolution of the system underneath the Hamiltonian. So we'll talk about between interactions that there's a time propagator, and that propagates the density matrix forward in time between different interactions. Yeah?
Well, what's the significance of like the duration of the pulse that comes in?
Right. In this particular case, the response function doesn't have any information about the light field. It's just a matter. So the light field comes in when you calculate the polarization. So there, if you missed the last one, the basic idea is that the polarization is a convolution in a multiple field convolution of the nth order response function with a sequence of fields, and it's an awfully messy expression. It's a product of all of the possible fields and when they act on the system. So the field profile goes in here. So there's a very, we'll get to the frequency domain version. You'll see that continuous field is very easy to deal with because these just take on continuous profiles, and that turns into the Fourier Laplace transform. Easy to describe. With real fields that have neither time nor frequency domain, there you put these really have the full profile of the electric fields, and typically you use the slowly varying envelope approximation. Apply an envelope to this and a carrier frequency, and then do convolution. And what makes that complicated numerically is you do have to watch the time delivery. Okay, so the other flavor of diagrams that tell you how things evolve are ladder diagrams. And these are effective when you've got multiple eigenstates of your system Hamiltonian. And now again, This encodes the propagation of the density matrix. Now time flows from left to right. We draw upward and downward arrows to identify absorption and emission events. In between each of these is a free propagation of the system under the material Hamiltonian. And because unlike other ladder diagrams, we are watching the density matrix. So there are two kinds of arrows. There are straight ones and dashed ones, and those are the ones that differentiate whether you're acting on the wrong artifact. So that's sort of the general flavor of all of that. So let me just put up this little chart online. This will keep me from actually drawing all of this out. Please. Okay, hopefully you can see this. This is basically meant to sort of summarize the range of possibilities that you can encounter in this kind of a diagram, sort of in shorthand. We can imagine that there are absorption and stimulated emission events. Those are the possibilities of the light field interacting with our driving system up or down. But then we do also have to keep track of relative phase. And when you're worried about the phase of one coherence relative to another, then we do want to differentiate wave functions and their conjugates. And their conjugates tend to be what we call draw-side interactions. Those also can have absorption and stimulated emission events. But of course, the relationships are all going to be conjugate. We draw inward pointing arrows for absorption, outward pointing arrows for emission, and they point depending on a sequence of events. For a particular sequence of processes, what we are interested in doing is adding the number of light fields in that correspond to a particular nonlinear experiment, propagate this density matrix through either the set of system eigenstates, and then make sure at the end that you end up in a diagonal element of the density matrix. Remember, at the end, after the sequence of events, you have to end up in a trace. So what we'll do is draw a sequence of arrows, and then at the end of that, the trace in a diagram is sort of put in symbolically by a wiggly line. It represents sort of the signal generation. The convention is that this is typically shown as a emission on the ket side. You could choose anything you want. If you don't choose a convention, then you end up drawing way too many diagrams. So this, let's see, I think the best way to sort of explain what this means is to work through some examples. Okay, so what happens is you'll end up with a diagram. And now a diagram represents one particular sequence of interactions from a set of levels that contributes to one of these correlation functions. As we'll see later on, we can select experimentally which correlation functions we look at, but we do need to then calculate all the possible permutations in which the light field can interact with these states. Then, given a set of diagrams, you'll see that these are very easily read off, and that you can write down the response function for your sample very rapidly. Then they just sort of shorthand notation for how the system responds. Not only that, but they carry with them a particular sign for the wave vector and frequency of the light going into the sample. And so when you add those all up, that tells you the direction of the color of the light field that's included. All right. So let's see, I think the best way to do this is just to run through some examples to get comfortable with it. Okay, let's start with the linear response function. We already know what to expect there. Linear response, we expect to see just a pair of dipole operators. There's one correlation function and its complex conjugate. That's what we expect. But now, how do we apply this, say, to a simple two-level system? We'll call this one. It's grounded and excited, and we'll say that we have a light field incident on the sample. It's linear spectroscopy, one light field, and let's start with that. So the step one is just to sort of identify the initial conditions. We're going to, you can imagine that we're going to start in the ground state, but you can imagine that it may be that you've got an energy, thermally populated states. You may have to keep track of starting in the excited state also. When we start in the ground state, we have one light field that can go in, and we think of that creating, an absorption process. So we draw that arrow up in a Feynman diagram. We'll start in the ground state population, and then I'm going to create an absorption process. What does that absorption do? It carries with it a transition from the ground to the excited state, and from this absorption event, GVE, it carries with it a dipole moment that looks like mu Eg. Actually, right, to start out with, it's good to, just to be rigorous about it, I'm going to scale this by the probability of starting in your ground state. Okay, now you're in a coherence. Now you're going to evolve with time. The light isn't there. The propagation is just dictated by the material Hamiltonian. So we're going to propagate under the material Hamiltonian. What we're saying then is we're going to apply time propagators to this EG coherence, which we just now, just for the purposes of running through an experiment to see what's happening, it's nice to use sort of a phenomenological type of factor to throw in here. So what I think is convenient to start is that you recognize that this is going to give you an oscillation e to the I omega g tau. But just to keep track of other dynamics, we'll just put in a phenomenological damping constant also. Minus gamma EG. A little bit later on, you'll see what we'll do is really this will get formulated in terms of the line shape function. All right, so that's the next step. We propagate forward in time. And now we've had one light interaction, and now that's the end of the story for linear. Now all we do is take a final trace over this oscillating dipole. Yeah, so physically the picture here is light went in and it created an EG coherence. This is an oscillating transition dipole evolving at the EG frequency. And that acts to radiate an electric field. So mathematically we draw in a emission from the bra on the Ket side of the density matrix. This is symbolically meant to reflect the final act of taking a trace of the dipole operator times the density matrix. But physically what it means is that we are returning the system to a ground state population, and that will lead to a diagonal element that we can trace over. Okay, so that emission that also carries with it the dipole operator, So we basically end up with something that is, pretty much exactly like we would expect. That this response looks like probability of starting in the ground state, a matrix element squared, and a time propagation. For the purposes of this experiment, now we want the response function. We know that we need R minus its complex conjugate. Okay. All that does is turn this into a sign. Right? So now all of a sudden, instead we've got probability at the ground state, UEG squared, sine omega EG tau, e to the minus gamma. Now, if you're really being careful about it, you would realize there's more permutations. There's the permutations of you starting in the excited state, and the light field stimulates emission down. And then the final trace actually involves an upward transition. So that, if you run through that, you get exactly the same factor. The only difference will be because let's see if I, is that it'll be scaled by the excited state population. And because the sign of the coherence in that case, rather than being EG, it'll be minus EG, or GE. That carries with it a minus. So, in the end, what you'll end up with is, the full expression that you sort of expect, which is, it's going to be related to the difference between ground and excited state. Now, this is a strange example. In principle, this diagram then tells you also about where the light field's going. In practice, there was one light field that went in, and it's an absorption event. So the light field in at plus e to the I k1 r minus I omega 1 t factor associated with it. That wave vector and frequency gets added into the polarization. Polarization is proportional to that, so that means that the signal is going to have to be proportional to this polarization. And so this immediately says that the signal wave vector is equal to the input wave vector, and the frequency is equal to the input frequency. So I mean, it seems trivial, but it says, yeah, if the signal's there, it just co-propagates with the light field, and it has the same frequency. Okay, that seems trivial. Let's try it for something a little bit. Let's try for something non-trivial. Let's go. Any questions? Yeah.
How do you think about absorption and fluorescence in this two-stage?
Okay. Emission is different. Think of emission very differently than fluorescence. So we don't want to deal with fluorescence. We'll call those the spontaneous processes, and we're just going to deal with sort of the semi-classical view of the light field, which is a coherent interaction of the light with the matter. So we'll call it stimulated emission. So we've got absorption processes, which take the energy. That's a little bit what's in this last column here. Absorption processes take the energy of the system up, increase the energy. What we're not keeping track of is the decrease the energy of the light field. Emission processes add, they take away energy from the matter, and then the conjugates, they made absorption takes it away, and stimulated emission adds. And then similarly, there's a contribution to the momentum of the matter from the light fields. Now, that's harder to see with linear spectroscopy. Let's try with the nonlinear one to kind of get a sense for it. Yeah.
Is it possible to get population in the excited state
Yeah.
with non-calls?
Oh, with what, right, but in this particular, if you take this particular view of how the system is evolving, to get population in the excited states actually requires two interactions with light field. But, that shouldn't be a surprise because, populations are always related to squares of, you always require a square of a matrix element to make an observation of a. So remember, each arrow here is related to one particular matrix element for an interaction. Okay, let's take a second order experiment. And let's imagine that we have a three-level system. And we're going to look just particularly at one we remember that we had two particular correlation functions. One of them we called Q1, and that like this. So what this is saying is this is you could just as well, let's say we start in the ground state, you could also write this as a correlation function. Sort of an equivalent way of writing that correlation function. It's just a sequence of interactions, each one of which acts to the right on this cat, followed by a sequence of time. So this is what we call, for bookkeeping purposes, you might think of this as a kind of correlation function. So we have two actions, and they both are on this side of the density matrix. So if you start in the ground state, and this happens to be the lowest energy state, your only choice with the first field is to go up. I could draw it up to F, or I could draw it up to E. Go up to E. This is an absorption process. It takes you to E. Use probability you start with G. You have a matrix element now. The next interaction also has to be on that same evolving state. We're going to, in this particular case, let's say we go up further. If there is a possibility, we can drive it down also. But let's just go up. Now this carries with, let's see, I'm sorry, there was a time propagation in between. If we look at what element of the density matrix you're in, EG, have 1 minus then there's the next transition matrix element, that's FE. And then we're going to propagate in a superposition of the F and the G states. During the period tau 2. Then we get to the end, we put our two fields in, and now we have to somehow take our trace after acting in the backlog. This allows us to go back to, say, the ground state. This is one signal that can come out that will close the loop, starting in a population and ending in a population. And that carries with it a GF transition matrix. So the important thing to remember is to end up in a diagonal state, take this trace. I could have drawn a signal that comes down to some other level, but that wouldn't have been summed over. Your trace or equivalently the equilibrium average. Now, there's also the possibility, there's many different permutations, right? I could imagine that there are emission events instead. I could also imagine now that, that there's the possibility that I could go up, absorb on one side and create an absorption on the other side of this density maybe. And that sort of involves acting on two separate coherences that have an opposite phase, opposite evolution of how they acquire phase. That sort of a process would involve starting at the ground state, sliding up to an EG coherence, propagating, and then absorbing from G to F. Then you would propagate in a superposition of the E and F states. And then you could take a trace after, acting on this transition. Just take it back. One thing I've left out telling you is that when it's quick to draw a bunch of diagrams, but in your signal contributions, one thing to remember is that at the front of all of these contributions, you want to put -1 to the n power. And the n power should be chosen to be the number of raw side interactions you have. So remember, going back to a commutator, there's a bunch of terms out there that involve minus signs. And those are the ones that have raw side interactions. So at the end of the day, some signal contributions will destructively interfere with others. And those will be the ones that differ in the number of these raw side interactions. In this particular case, we have none. In this particular case, we have one. Okay, any questions so far? Let's go back to this guy for a moment. From a ladder diagram, this immediately tells you the frequency of the signal, right? I put in plus omega EG, and I add omega FE. My signal has to come out of the sum of those input frequencies. So I immediately know that my signal frequency equals omega FE plus omega EG. That's just omega FG. Okay, so my signal comes out of this gap. I can similarly write the same thing for my wave vector, for which how this signal propagates. The signal will also propagate. Upward transitions involve, or rather, absorption on the head involves positive momentum. So we have two fields, each going up, each adding positive momentum to the system. And the signal then is going to be dictated by the sum of those incident wave vectors. So imagine you have two fields that are coming in linearly. We sum those two wave vectors, then signal will have to come out at the sum of those two. That sort of tells you that it's propagating. It will also propagate. You can imagine crossing these peaks. Now the sum of those wave vectors propagates at a unique angle, and that would tell you the direction of the light should go. All right. Yeah.
And it's possible that some of these dipole operators are at 0 or very small.
Right, exactly. So, well, you put them in there, and then that will scale the magnitude of the response. If it's 0, right, you're going to throw it in. there's a, so, right, all your selection rules are buried in that. Okay.
So how would this change if you were observing, say, a signal downward transition from F to E instead of from F to G?
F to E instead of F to G. Okay, in this particular case, this would, let's see. That's a good question, because that's sort of turning it around on its head. And experimentally, I'm looking at light that's emitted over here. Or experimentally, I'm looking at light that's emitted here. Okay. So how do you get that? As it turns out, in this particular example, there's no way to get it. And you need more interaction. So the idea is, I can connect those. This is one way that I can connect those. I can create a superposition of F and E, and in principle, generate light at that signal. It's a difference frequency. And so that I can work backwards. What allows me to do that? The other draw. There's a bunch of permutations about how you can generate that. And these are complex conjugates. So in practice, those are the diagrams. You would have propagation under this coherence and that coherence that emits the signal. As it turns out, for second order experiments, you find that when you average all of these, well, there's an orientational factor in the response function, which we'll talk about later. It averages to zero. Second order responses require non-central symmetric medium. But this is the basic idea of difference frequency. Typically, if you talk about something like stimulated emission or pumping, that actually sort of involves in this type of a language, a lot more interactions. Really involves creating populations inside of one, and then acting to drive them down. That falls into the class of third order experiments. I'll point that out. Okay. Any questions?
This is the issue with phase matching, right? If you're having the non-coding arrangement, then you can't add up your momentum vectors to give you the right. Okay, so in general makes sense.
Exactly. So the issue there is, and that's right. We do have to talk about what is the wave vector for the polarization, and that really is just the incident fields, right? So that looks like the field that's radiated, that also that requires the phase matching, and that depends on the polarization and the sync of the wave vector mismatch. There's AR over here also. That depends on the wave vector mismatch, and so this is a perfect example. Exaggerate. Let's see. Okay. This is the thing we have to remember is that momentum conservation says that the signal is going to come out in this direction. But energy conservation says that the signal comes out at the sum of those frequencies, and we also know that the magnitude of the wave vector is going to be so the length of the wave vector is actually going to be dictated by the frequency conservation, or it's going to be much longer. Matches perfectly in a collinear geometry, and as you twist the angles, you get a phase matching mechanism to increasing this. Yeah, that's the efficiency. All right.
And I'm sorry, I just got confused.
Yep.
So, energy conservation still has to apply.
Yep. This all really has to do with efficiency.
Okay. So where does the extra energy, or where does the energy defect go?
In the end effect, these are all Fourier transform relationships. Your ability, so, if we're talking about time frequency complementarity, your ability to dictate the frequency is all dependent on your time resolution. So this is just a space manifestation of the same thing. Your ability to determine the wave vector is dictated by how much path length you have to propagate through. So, your ability to be efficient in generating the signal and propagate it into a direction depends on how well matched those are and how long your sample is. If you have a thin sample, it's relaxed. If you have a long sample and well-defined frequencies, it's very strictly conservative. And
Okay. What if you go through a thin sample many times?
I mean, you have, it's all dependent on whether you maintain coherence.
Coherence through the, okay.
But what this is saying is, look, if, in this particular case, if you cross two beams and try to look at that direction, the wave vector mismatch is probably big enough that you won't see anything. Because this delta K is much greater than, sort of the dimensions of your sample. It just won't happen. Right? You can't conserve the momentum or the energy. One to the other.
How does this issue solve your box area?
It's excellent question. If you don't mind holding on to that, that's one of the things I want to talk about. I was thinking we could take a break now. And I want to talk about third order spectroscopies and I'll tell you a bit about boxes. All right, so why don't we break, say, call it 10-15 minutes?
Due to technical difficulties, only a portion of this lecture is available.